And so just to kind of help understand where these operators come from, I'm just going to quickly go through again how would he get the operators or symmetry elements for two-fold, four-fold, and a mirror plane. And it all has to do about how the x and y coordinates, for example, if this was two-dimensional space, how they change. So for example, if we look at a two-fold symmetry, so if we were to rotate the x unit vector here 180 degrees, the new x coordinate would be negative. So you would write this, if we were going to write it, we would say x 0 when we rotate it 200 degrees becomes negative x 0. And if we did the same thing to the y coordinate, so let's say what happens when we rotate the y coordinate 180 degrees. So we take this unit vector, that's the unit vector for the y axis, we rotate it 180 degrees. You see that our initial coordinate y 0 becomes negative y, or excuse me, let me erase. I should write it 0y, my bad. Let's see. So 0y becomes 0 negative y. And that's why when we have a two-fold rotation, let's say parallel to the c-axis, xy become negative x negative y. And that's where the negative x negative y comes from, is because when you rotate, and you're always rotating it counterclockwise. So when you rotate the what's called the unit vector x 180 degrees, you see that it becomes negative. And when you rotate the unit vector y 180 degrees, you see that the y component becomes negative. And so sometimes they use matrices to show this. So see here, this is the x and the y component, and that's where we get the negative x negative y. And so for a two-fold along the z-axis, when you rotate parallel to the c-axis or the z-axis, that is why x and y become negative. So that's how they get the negative x negative y for a two-fold symmetry. Now we're going to apply that same kind of concept to four-fold symmetry. So for four-fold symmetry, we're going to start with x and 0, so the unit vector of x. If we rotate it 90 degrees, so we take the x unit vector, rotate it 90 degrees, you see that now x became y. So now when we rotate 90 degrees, we get y 0. Because again, when we rotate this x unit vector 90 degrees counterclockwise, we get that it becomes y now. So we go from x to y. That's our new coordinate when we rotate the x unit vector 90 degrees. Now we do the same thing with the y unit vector, the 0, 1. So we take the y unit vector, which is y0, and we're going to rotate it 90 degrees. So here we take the y unit vector, we rotate it 90 degrees. You see that now y has become negative x. I wrote this backwards, 1 second. Write it correctly. So we have 0y. When we rotate it 90 degrees, the new y coordinate is 0 negative x. Because again, we rotate the y unit vector 90 degrees counterclockwise, you see that we end up at the negative, it becomes negative x. So we go from 0y to 0, negative x. And so when we write the overall symmetry, we get x, y gives us y negative x when we rotate 90 degrees. And so they can illustrate this as a unit vector, or excuse me, as a matrices like this. So here we have the x component. Wait. Y. So this is x. I did it wrong, yeah. And this is y. So over here, this is x. This is y. And so the way you would use these matrices is you could take your fractional coordinates, say it's 0.2, 0.3, and you would multiply this row by this column. You would get negative 0.2, and you multiply this row by this column, you get negative 0.3. So that's how you can use matrices as well to determine the symmetry related positions. The same thing here, you can take this matrices for the fourfold symmetry, multiply by a set of coordinates. So we'll say 0.2, 0.3. So this is our xy coordinates. So here we have x and y. So the first, this would equal, so we go across and down. Second, I made a y negative x. Y becomes, oh, son of a, hold on. Give me 1 second. X. That's right. This is not right. 0y rotate 90. X0 rotate 90 degrees becomes negative y 90 degrees, x 90 degrees, 0, 1. Yeah. This would be 0, x. All right. X becomes y. All right. And then we have 0, y. I'm just correcting. This is, as you can determine, it's very tricky. 0x, so x becomes y, that's good, and then y becomes negative, or negative, y becomes negative x, that would be 0. And then when we add them, you get this. So now that makes better sense. This would be negative 0.3 and 0.2. Now, if this was a three dimensions, you would just have an extra set of zeros here, and at the bottom, since it's parallel to C, it would be 0, 0, 1, and 0, 0 here. So C value, the Z value won't change if it's 3 dimensions. And then a mirror plane is along a plane. So if it's 2 dimensions, if we have a mirror plane along Y, that means that X is going to reflect, and it's going to become the negative of that. And that's where they get a matrices for the mirror planes as well. So that's where we ended up, or left off on yesterday. Now we're going to continue, and we're going to look at 3-fold and 6-fold rotation. Now with 3-fold and 6-fold rotation, we have to introduce a different type of coordinate plane. So it's not the Cartesian coordinate anymore. It's one that was made specifically for 3-fold and 6-fold symmetry. So here we have the 1, 0. So this is the x-axis, this is the y-axis, and then this is the combination of the x and y where we get -1, -1. And so here what we want to look at is if we rotate, since this is x and this is y, if we rotate x 120 degrees, so if we start at x 0 and we rotate 120 degrees, we get now that x has become y, like that. So when you rotate 120 degrees, the x now becomes y, and that's why you see it's flipped. Now if we rotate the y value 120 degrees, so we have 0 y, now we rotate, we get 0 is, the new y value is this -1, -1 means that it's -x plus -y. So we would get just be -x and -y. Because when you take the y unit vector, the 0, 1, and you rotate it 120 degrees, now you get -x, -y, just like we have here. So if we were to write these together, so the new x is, so we would get, let's see, x, y equals -x and x plus -y. And that's the symmetry operator for a 3-fold rotation. So this is the x and this is the y. And if we look down here, this is what it looks like. Hot dog, I got it backwards again. -y, x plus -y. That one's right. X, y becomes. Okay. Just this, for some reason I put -x, 0, y, unless they're both, oh, okay. Because when we rotate the unit vector 120 degrees, the y becomes negative y, negative y. So that's where we get negative y and x plus negative y. So this is the x, this is the y. So again, when you rotate 120 degrees, the x becomes y. When you rotate y 120 degrees, it becomes negative y, negative y. And then when you add these two together, you get the 0x and negative 1, negative 1. And so you get that x is negative y, and y is x plus negative y. And then if this is a parallel to C, and then you would just have z out here. So you would have an extra row like this. That's if it's a threefold parallel to C. Now if we come over here to the sixfold symmetry, if we rotate the x unit vector 1, 0, 60 degrees, we get that x becomes xx. And then if we rotate y 60 degrees, we rotate y 60 degrees, it becomes a negative x. So we get negative y 0. And so now when you get these two together, you get that x, y transforms into x plus negative y, comma x. And that's where you get the two matrices here. This is x, this is negative y. So you would add these two to get the x value, and then this would be just x here. So this is the x, and this is the y. Now let me undo that. So I'll give you a second to kind of write down these operators, because we're going to do some examples of this in just a moment. Let me write them down as well. So here we want to perform the following operations on these sets of coordinates to kind of review about symmetry operations. And so first we have a mirror plane perpendicular to A. So we want to take these sets of coordinates and perform a mirror plane perpendicular to A. So when we take 0.2, 0.3, 0.7, perform a mirror plane perpendicular to A. Since it's perpendicular to A is the coordinate that becomes negative. So it'd be negative 0.2, 0.3, 0.7. Next we have a twofold parallel to B. So the parallel to B tells you the axis about which we're going to rotate about. So it's the B axis. So we're going to start with 0.2, 0.3, 0.7. Since we're rotating about the b-axis, that means that the b coordinate or the y coordinate doesn't change, so we get negative 0.2, 0.3, negative 0.7. So that is a twofold parallel to B. Now the rest of them we're going to do parallel to C because A, the matrices that we used were based on parallel to C, and B, the unique axes for most of these crystal systems where you have the fourfold, threefold, or sixfold is typically C axis. So it makes sense to practice with those parallel to C axis. And so here, if we look, we have a fourfold parallel to C. If we remember, a fourfold parallel to C is y negative x z. That's the operator. So we start with our initial set of coordinates, 0.2, 0.3, 0.7. We perform the first 90-degree rotation. We get 0.3, negative 0.2, 0.7. So that's 190 degrees. Now we do another 90 degrees. We get negative 0.2, negative 0.3, 0.7. So now we're done 180 degrees. Now if we do another 90 degrees, we get negative 0.3, 0.2, 0.7. So each time I'm taking the set of coordinates and applying this operator, y negative x z, to it. So when we have 0.3, negative 0.2, 0.7, the new x is the previous y value. That becomes negative 0.2. The new y is negative of the previous x value. That's where the negative 0.3 comes from. And then, of course, 0.7. If we do one more rotation, we should end up back where we started. So that would be 0.2, 0.3, 0.7. So for a fourfold, these are the four symmetry equivalent positions. So when you do a fourfold, you have to do 4 rotations. So that's fourfold parallel to C. Now we're going to do a threefold parallel to C. And again, our operator is negative y, x minus y. I mean, x plus negative y is the same as x minus y. And then we have z. So we start with our initial coordinates, 0.2, 0.3, 0.7. We do a threefold rotation. So we have negative 0.3. X minus y is negative 0.1. And then we have 0.7. So that's the first 120-degree rotation. Now we do another threefold rotation, another 120 degrees. So again, the new x is negative y, so we get a 0.1, and then x minus y. So negative 0.3 minus a negative 0.1 would give us negative 0.2, and then of course 0.7. So now we're at 240-degree rotation. Then if we rotate again, we should come back to where we started. So the new x is negative of the previous y, so that becomes 0.2. And then the new y is x minus y, so 0.1 minus a negative 0.2 is 0.3. And then we get, of course, 0.7. And so for a threefold rotation, there are 3 symmetry equivalent positions. And the way you know if you do it right is that you come back to where you started with for rotations. So if we keep on rotating counterclockwise 120 degrees, you'll get back to where you started. Now let's look finally at a six-fold rotation. And for a six-fold, remember our operator was x minus y, x, and z. So we're starting initially with 0.2, 0.3, 0.7. And we're going to perform a 60-degree rotation. So the new x is x minus y, which is negative 0.1. The new y is x, so that's 0.2, and then z. Now we do another 60-degree rotation. The new x is the previous x minus the previous y, so negative 0.1 minus 0.2 gives us negative 0.3. The new y is the previous x, negative 0.1, 0.7. So now we've rotated, you could say 120 degrees. And just for illustration purposes, notice that the 120-degree rotation here is exactly the same as the 120-degree rotation here. Now continuing with another 60-degree rotation. So again, it's x minus y, so negative 0.3 minus a negative 0.1, we get negative 0.2. The new y is the previous x, so that's negative 0.3. And then we have 0.7. So with a six-fold, we have to do it 6 times in order to get back to it. So we rotate 60 degrees again. So the new x is our previous x minus the previous y. So negative 0.2 minus a negative 0.3 gives us 0.1. The new y is the previous x, negative 0.2 and 0.7. And again, just for comparison, if we look at our threefold, the third position in the threefold is the same as this position because they're both 240-degree rotations. Now if we rotate again 60 degrees, our new x is x minus y. So we have 0.1 minus a negative 0.2, we get 0.3. Our new y is the previous x, so 0.1, 0.7. Now we do another rotation. The new x is x minus y, so that would be 0.3 minus 0.1, we get 0.2. The new y is the previous x, 0.3 and 0.7. So notice that we came full circle in a six-fold rotation. So we have 1, 2, 3, 4, 5, 6 symmetry equivalent positions when we have a six-fold parallel to C. And notice how we came back around to our original set of coordinates. Sorry about that. I'm in the X-ray lab today if you hadn't seen the X-ray machine behind me. So this concludes rotations. Now we're going to look at roto-inversions. Roto-inversions and, excuse me. roto-inversions, and screw axes and glide planes. So a roto-inversion is just a rotation and a inversion. So all we're going to do is we're going to take these operators that we have for a 4-fold parallel to C, a 3-fold parallel to C, and a 6-fold parallel to C, and we're going to implement the inversion center on them to get a new type of operator. And this is just kind of an overview of all the different rotational axes, and these are the operators for them. So if you, this is a good chart to refer back to when you're doing the symmetry operations. And so I'll post this new document up once we finish today's lecture. I'll post a new PowerPoint with this updated, and so you can refer back to it. It's also in the electronic textbook if you've done any reading there. Okay. So now talking about roto-inversions. And so roto-inversions means we have a rotation, and then we do an inversion center to generate symmetry equivalent points. And so we have usually denoted with a number and a line above the number. So that indicates it has an inversion center. So some of the common types of roto-inversions are 3-fold, 4-fold, and 6-fold roto-inversions. So here in this ethane molecule, what we do first is we rotate 120 degrees, and then we apply the inversion center to it. So for example, if we look at these coordinates that we used last time, 0.2, 0.3, 0.7, and let's say we want to do a 3-fold roto-inversion parallel to C-axis. And we want to generate the first set of coordinates. What we're going to do is we're going to do a 3-fold rotation parallel to C. So that would be negative 0.3, x plus negative y, negative 0.1, 0.7. And then we apply an inversion center. So that means we take our coordinates and we take the negative of it. So then it would become 0.3, 0.1, negative 0.7. And so this would be the coordinate, you could say number 5, shown in red. So you have to do two things. You have to do a 3-fold parallel to C, and then you have to do the inversion center. And then you would keep on doing this until you generated all these symmetry equivalent points. So you have to do both of them together. So this would be, if this is the first point, this would be the second symmetry related point. So again, it's a rotation followed by a inversion. So what you can do is, if you wanted to know the actual operator, a 3-fold parallel to C is negative y, x plus negative y, z. So this is a 3-fold. Now if we want to know what a roto or 3-fold inversion is, parallel to C, you just take everything and make it negative. So instead of negative y, it's y plus negative x, negative z. And that's how you can get the actual symmetry element for a 3-fold roto inversion. All right. So this is just showing you how they go through each set of symmetry related points. So the first step, they do a threefold rotation. Then they do an inversion center. Then they do a threefold rotation on those coordinates, and then another inversion center. So they keep on doing rotation and then inversion center to generate all the equivalent positions. Now, roto-inversions are important because they help kind of give us what we call identifiable polyhedrons. So different types of shapes can form from roto-inversions. And so one thing to remember is that for odd number roto-inversions, usually imparts a center of symmetry. And what that means is that, and this is very important, odd number roto-inversions have an inversion center. So these are centrosymmetric. So to be centrosymmetric, one criteria is you could have a odd roto-inversion. Then it's going to be centrosymmetric. Notice that if it's even number roto-inversion, and the only even number roto-inversion there is a fourfold, that these are non-centrosymmetric. So odd numbers are centrosymmetric, evens are not. And another example of an even is a sixfold as well. So if you have a fourfold or sixfold roto-inversion, they do not have an inversion center. They're not centrosymmetric. I know it sounds kind of backwards if it's a roto-inversion, but if it's for a fourfold or sixfold, there's no center or symmetry, aka inversion center, in it. Only the threefold has a center of symmetry. So it's going to be centrosymmetric. All right. So what do you think? You would probably ask, well, why isn't there a twofold roto-inversion? And if we have a twofold roto-inversion, it's actually going to be the same as if we just had a mirror plane perpendicular to B. So let's look at a twofold roto-inversion. Here's. We want to perform a twofold roto-inversion parallel to B with these coordinates, say 0.2, 0.3, 0.7. So what we do first, we do the twofold parallel to B. We get negative 0.2, 0.3, negative 0.7, and then we do the inversion center, which would be 0.2, negative 0.3, 0.7. So this is a twofold roto-inversion. Now let's do the same thing, but we're going to do a mirror plane perpendicular to B with the same set of coordinates. So if we have the same set of coordinates and we do a mirror plane perpendicular to B, that means B becomes negative. And this is why we do not have twofold roto-inversions, because as you see, we get the same thing as a mirror plane perpendicular to B. So you will never have a twofold roto-inversion. Now we're getting into, so that concluded the point symmetry, the rotations, roto-inversions, mirror planes. Now we're getting into space symmetry. So here we're combining a point symmetry with translation. And the first one is a screw axis. So a screw axis incorporates the point symmetry rotation plus some translation with it. And so the way we get the rotation is, it's always written the rotation and then the subscript is m, and the translation is always m over n. So if you take your hand, just like in the picture, if you rotate it 180 degrees and translate it up half a unit, you get the second hand starting from the bottom. And then if you rotate your hand again 180 degrees and shift it up, you get the third hand at the top of the diagram. And so if we have a 2/1 screw axis, the 2 represents the rotation. So the 2 represents the rotation, and then 1/2 represents translation. So if it's a 2/1 screw axis along B, that means we rotate along the B axis and then translate along a half a unit along the B axis. So if we were to look at a set of coordinates, let me write it down here. If we had 0.2, 0.3, and 0.7, and we do a twofold parallel to B, 2/1 parallel to B. So again, we rotate along the B axis. So that becomes negative 0.2, 0.3, negative 0.7. And then we translate along the B axis. So we add 1/2 to the Y coordinates. So we get negative 0.2, 0.8, negative 0.7. So again, this is the symmetry equivalent position. So you do the twofold and then you translate along the Y axis. Now if we were to do this one more time, so we do a twofold parallel to B, and then we add 1/2 to the Y coordinate, we get. So notice here, this is very important. Notice that if you keep on doing the screw axis, eventually you'll get back to the same X and Z coordinate. However, the Y coordinate has been translated 1 unit cell over. So with screw axes and glide planes, you don't end up back at the original set of coordinates. You'll end up, 1 or 2 units translated along a particular axis. And so the symmetry operator for a screw axis, 2/1 parallel to B, would be negative X, Y plus 1/2, negative Z. Now, if we had a force of 3 screw axis along C, that means we do our 4-fold rotation about the C axis, just like we did in the previous example. However, we need to translate 3 force along the C axis. That means we got to add 0.75 along the C direction. So now if we come back to our set of coordinates, 0.2, 0.3, 0.7, and we want to do a force of 3 parallel to C. So what we do first, we do our 4-fold rotation. So remember, 4-fold is, what was it? It was Y negative X Z. So the new X is the Y value, negative X Z. So this is the 4-fold rotation. Then we're going to add 0.75 to the Z coordinate. So then it becomes 0.3, negative 0.7, 1.45. And so this is the symmetry equivalent position for the first position of a force of 3 screw axis. And if you were to write the symmetry operator, it would be y negative x z plus 0.75. And so what this bullet is saying here is you won't reach an equivalent point until you do both the rotation and translation together. So just doing the rotation is not going to generate an equivalent point for a screw axis. You got to do a rotation and then the translation together. That's your equivalent position. So don't forget to do both the rotation and then the translation. Very important. And so what the last bullet is saying is if you keep on doing the screw axis, you're going to move a point a total of m unit cell lengths. So for example, if our 2 sub 1, that means we're going to move 1 point on there, 1 unit cell length. If it was for example, the force of 3, we would keep on doing it. Eventually, when we got back, we would have moved the z-axis, z-coordinate, 3 unit cells over. So if you keep on doing a 2 sub 1 parallel to B, the y-coordinate will be shifted 1 unit cell. If you keep on doing a 4 sub 3 parallel to C, eventually the z-coordinate will be shifted 3 unit cells. So that's what the last bullet is saying is if you keep on doing this, one of the coordinates is going to be shifted by the m number of unit cells. This is just showing you step by step the symmetry operators for each one. So here we have a 2 sub 1 parallel to B. We do a rotation about the B axis and then a translation. And the first two are showing you that if you keep on rotating, actually this should have been, you would have had y plus 1. Because eventually you would get x, y plus 1, z, once you've done this 2 sub 1 parallel to B twice. The same thing if you have a 2 sub 1 parallel to A, if you do it again, you would get x plus 1, y, z. Okay. So here we want to perform a 2 sub 1 parallel to B for the coordinates 0.2, 0.3, and 0.7. And what I'm going to do is I'm going to do it all together, the translation and the rotation. So remember, 2 sub 1 parallel to B. The operator is negative x, y plus a half, negative z. And so this would become negative 0.2, 0.8, negative 0.7. If we were to do this one more time, we would get 0.2, 1.3, 0.7. So we shifted the y coordinate 1 unit cell. Okay. And just showing you some 3 sub 1, 3 sub 2 screw axes. So for a 3 sub 1, you rotate 120 degrees and then you translate along a particular axis by 1 1/3. Or it could be a 3/2, just means that you still do the threefold, but you translate 2/3 instead of 1/3. And with the 3/1 and 3/2 screw axes, you can actually form what are called enantiomorphic pairs. So one will be right-handed and one would be a left-handed enantiomer. And the same goes for 4/1 and 4/3, or 6/1, 6/5, or 6/2, and 6/4. So these can generate different types of enantiomers or enantiomer pairs, depending on which screw axis you use. We talked about this. All right. And this is just showing you a 4/1 along C. These are the symmetry operators. So again, we're still doing the negative yx. We add a fourth to the z axis. Once we get to the last rotation, the z would be translated 1 unit. So this should be +1. Now it's common in crystallography that we don't put the z +1 because it's the same thing as z. So that's why you don't see it in this diagram. But remember, since it's 4/1, that means that the z coordinate is going to be translated 1 whole unit when you work through all the different symmetry equivalent positions. Okay. So now we want to perform a 4/1 parallel to C for the following set of coordinates. So we have 0.2, 0.3, 0.7. And remember, our symmetry operator for this is negative y x z plus 1/4. So that's what we're going to be doing each time. So first, negative y, so negative 0.3, 0.2, and then 0.7 plus 0.25. We get 0.95. That's the first equivalent position. Now notice, since it's 4/1, by the time we finish, the final z coordinate would be 1.7 because it's going to translate 1 unit cell. So then we do the same thing again. Negative y becomes x, x becomes y, and then we add 0.25 to z. And we get 1.2. Then we do another 4/1 screw axis. X is negative y, so 0.3, negative 0.2, and then z is 1.45. And then we do it one more time. We get 0.2, 0.3, 1.7. These are all the symmetry equivalent positions shown here. Now when you get to this one, the last one, that means we've kind of cycled all the way through. So now you're starting in a next unit cell, and then you would do it again to generate those equivalent positions. So again, when we do a 4/1 parallel to C, you do the 4-fold rotation, and then you just add 1/4 to the z coordinate each time. Okay. The last space symmetry that we're going to discuss, and this will actually conclude all of the symmetry we'll be talking about, is glide planes. And glide planes are a reflection which is the point symmetry plus translation. And you can think of a glide plane if you stand up and you cut your body in half, and then half your body moves along a particular axis, that would be a glide plane. So again, it's a reflection, then a translation. And so the orientation of the plane will be specified by saying perpendicular to B or perpendicular to A or perpendicular to C. Whatever it's perpendicular to, that's what becomes negative. And then the letter in front of it is what is translated by. So you can have axial glides, which are along a particular face, a half a unit. Diagonal glides, which are what we refer to as end glides, so it's along a face diagonal. So two of the axes are translated along. And then we have diamond glide, which is referred to as D, which is the fourth translation along every direction. So let me show you just a few examples of these. Let's say we have the following set of coordinates: 0.2, 0.3, 0.7. And we want to do a glide perpendicular to C, N glide perpendicular to B, and a D glide perpendicular to A. So we're going to do an A glide perpendicular to C, N glide perpendicular to B, and a D glide perpendicular to A. So an A glide perpendicular to C, since we're an A glide, that means we add a half to the X value. So it becomes 0.7. 0.3 is Y. Y doesn't change. And then since we're perpendicular to C, C becomes negative. So negative 0.7. So those would be the coordinates for an A glide perpendicular to C. Now if we do an N glide perpendicular to B, now pay attention here, this is important. N glide means that you add a half to the other axis that is not B. So we're going to add a half to A and a half to C. So this would become 0.7. Now since it's perpendicular to B, B becomes negative. And then we add a half to the C. So it becomes 0.7, negative 0.3, 1.2. And then lastly, a D glide perpendicular to A. It's a diamond glide, so everything gets a 1/4 translation. Now, since it's perpendicular to A would become negative, so it'd be a negative 0.2 plus 0.25, it would be 0.05. And then 0.3 plus 0.25 would be 0.55, and then 0.95. So that would be a D glide perpendicular to A. So again, the D glide means every axis gets a 1/4 translation. The A would become negative. So it'd be 0.25 minus 0.2. That's where the 0.05 comes from. And so you may say, well, why do we have glide planes? So in this illustration, it's showing you that glide planes can improve molecular packing. So it'll be able to pack more efficiently as a glide plane versus if you just had a reflection plane. So we talked about axial glides. So axial glides, you're translating along one of the faces. And what you translate by is the letter that comes first. So a B glide perpendicular to C means you translate along the B a half a unit, and C becomes negative. And so you can have a B glide perpendicular to C, you can have a B glide perpendicular to A, but you cannot have a B glide perpendicular to itself. That doesn't work. You can have a C glide perpendicular to B, a C glide perpendicular to A. What you need to remember is that whatever it's perpendicular to, that's what gets the negative sign. So B glide perpendicular to C, C gets the negative sign, B gets the translation. So for n-glides, again, n-glides, the axes that are not perpendicular get the translation. So an n-glide perpendicular to A means A becomes negative, the other two add a have to. N-glide perpendicular to C means C becomes negative, and the other two get translation. So these are called n-glides or n-glide planes. And then lastly, diamond glides, depending on what you're perpendicular to, it becomes negative, but what you have to remember here is that every coordinate has to be added a fourth to it. So it's a mirror plane and then a translation. Every coordinate gets a fourth translation to it. So those are the types of glide planes you can have. So what I want to do here, just to finish up, do some more examples. So what we have is a C glide perpendicular to B, an A glide perpendicular to C, and an N glide perpendicular to B. And we'll also do a D glide perpendicular to C for these 0.2, 0.3, 0.7. So we have 0.2, 0.3, 0.7. We do a C glide perpendicular to B. So what does this mean? This means that A doesn't change, B becomes negative, and C we translate by half. So that is a C glide perpendicular to B. Let me number these. So this is 1, 2, 3, 4. This is number 1. Number 2, we have an A glide perpendicular to C. So an A glide perpendicular to C means A gets translated by half, B doesn't change, and C becomes negative. Next we have an N glide perpendicular to B. So since it's perpendicular to B, that means A and C get translated and B becomes negative. Again, we're translating by half for axial glides and N glides. And then number 4, we have a D glide perpendicular to C. So we start with 0.2, 0.3, 0.7. So since it's D glide perpendicular to C, we translate a quarter for A and B, and then for C we got to change the sign and then add 1/4 to it. So we get 0.45, 0.75, and then you make 0.7 negative, add 0.25 to it. We get negative 0.45. So that would be a D glide perpendicular to C. So that concludes today's lecture on symmetry and actually finishes up symmetry operators or symmetry elements. Tomorrow we'll be talking about space groups and how all these symmetry elements come together to form a particular group. And there's roughly 230 different space groups. But you'll be surprised that we only actually encounter roughly about 6 or 7 of those space groups on a routine basis. A lot of them we hardly ever encounter when doing real crystallography. So I'll go ahead and stop the lecture. If you have any questions, feel free to ask in the chat box or in the